In this section, we're going to solve systems of linear equations in two variables. Over here, I've written the first one. It's a system that consists of 3x minus 5y equal negative 2 and 2x minus 3y equal 1. The system consists of two linear equations in two variables. Now, each of these equations has a graph that's a straight line, and we're assuming when we solve this system that those two lines intersect in one point. And what we're after is the coordinates of that point. Now, we're going to solve this system by adding the left sides and the right sides together, and we want to do it in such a way that either x is eliminated or y is eliminated. So let's start by eliminating y from this system of equations by first making these coefficients equal to each other. Let's see, if I get a negative 15 here and a positive 15 here, when I add these together, the y's will be eliminated. So I'm going to start by multiplying my top equation by 3. 3 times 3x, 9x. 3 times negative 5y, negative 15y, and then 3 times negative 2, negative 6. Now, the bottom equation I'm going to multiply by negative 5 so that I end up with a positive 15 in front of y. Negative 5 times 2x is negative 10x. Negative 5 times negative 3y is going to be positive 15y. And then that will be equal to negative 5 times 1, which is negative 5. Now, this system of equations that I've written right here is equivalent to my original system because it consists of simply using the multiplication property of equality on each equation. So I know that it has the same solution set as my original system. But now when I add the left sides and the right sides together, that's an application of the addition property of equality. You see this variable y will add to 0 or be eliminated from the system. So now I do that addition, and I have 9x plus negative 10x is negative 1x. Plus 0y is equal to negative 11, negative 6 plus negative 5. Now, if I multiply both sides by negative 1, I end up with x equal 11. Now, that's the x-coordinate of the point of intersection of these two lines. To find the y-coordinate, I'll take this 11 and substitute it back in for x in any one of these original equations. Let's try this equation. So I'll substitute x equal 11 back into this equation. I'll have 2 times 11 minus 3y is equal to 1. That's 22 minus 3y is equal to 1. I'll add negative 22 to both sides and have negative 3y is equal to negative 21. So y will be equal to negative 7. Take that back, positive 7. When I divide negative 21 by negative 3, I get positive 7. So here is my solution to this system of equations. X equal 11, y equals 7. It's an ordered pair whose coordinates satisfy both equations. Now, if I was to graph both of these equations, you would see that they intersect at the point 11, 7. Let's look at another system. 4x minus 3y is equal to 2. 8x minus 6y is equal to 4. Let's eliminate x from this system, and I can do that very simply by multiplying this top equation by negative 2 and adding it to the bottom equation. So this I'll multiply by negative 2. So that means times negative 2. So I have negative 8x plus 6y equals negative 4. The bottom equation, I'll just have no change in it. So it's 8x minus 6y is equal to 4. Now look what happens when I add the left and right sides of these equations together. Negative 8x plus 8x is 0. 6y plus negative 6y is 0. So I have 0 equal to negative 4 plus 4, which is 0. I end up with both variables being eliminated and a true statement. That means that these two lines here coincide. Any solution to one of them is a solution to the other one. Their graphs are exactly the same line. So in this case, we say any ordered pair that satisfies one equation satisfies the other. We have an infinite number of solutions to our system, and we call it a dependent system of equations. If, on the other hand, we had gotten a false statement here, that would be an inconsistent system, and that would mean that the two lines were parallel and had no points in common. Here's our next example. 1/2 x minus 1/3 y equals 2. 1/4 x plus 2/3 y equals 6. Now, I think it would be easiest if we eliminated these fractions in the beginning, so I'm going to do that. This equation I'm going to multiply through by 6, so I end up with 3x minus 2y is equal to 12. This equation I'll multiply through by, what do I need here, 12, the least common denominator, so that I can eliminate all the fractions. 12 times 1/4 x will be 3x. 12 times 2/3 will be 8y. And then 12 times 6 will be 72. Now, I'm not going to go any farther with this system of equations, but you can see now it's set up to solve like we've solved the previous two systems. So if you have a system that has fractions to begin with, you can eliminate the fractions with the multiplication property. Here's another example. The system consists of 2x minus 3y equal negative 6 and y equal 3x minus 5. So this system is set up to solve by the substitution method. So I'm going to take this expression for y from the second equation and substitute it for y into the first equation. When I do that, I have 2x minus 3 times y, which is 3x minus 5, is equal to negative 6. So essentially, I've done the same thing as I did before. I've eliminated one of the variables from this system of equations. Now I'll simply solve this for x. 2x minus 9x plus 15, when I multiply through by negative 3, equals negative 6. 2x minus 9x is negative 7x plus 15 equal negative 6. Negative 7x is equal to, I'll add negative 15 to both sides and end up with negative 21. So x is equal to 3. So x is equal to 3. To find y, I'll take this value of x and substitute it back into this equation to get y is equal to 3 times 3 minus 5. That'll be 9 minus 5, which is 4. So y is equal to 4. My system has a solution, the ordered pair x equal 3, y equal 4. That's the solution to this system of equations. This method of solving the system is called solution by substitution. I substitute this expression for y from the second equation in for y in the first equation. That gives me this, which I solve for x, then back substitute and get the corresponding value of y.